Okay, group 7, the halogens. So you can list their symbols from the top: fluorine, chlorine, etc. Just to become familiar with them. They're in group 7. They've got 7 electrons in their outer shells, regardless of what happens in the inner shells. This is something that catches pupils out sometimes. If I say how many electrons in the valence shell of iodine, you're going to say 7. Astatine, 7, because they're in group 7. And because of that, they need to gain 1 electron to get a full outer shell. So typically, they exist as diatomic molecules in their elemental form. So they form this single covalent bond just so they both get to a little bit more of a stable situation. You can have a go at the iodine molecule. It's going to be very similar. Obviously we can do it a little bit bigger because iodine atoms are bigger. And the single covalent bond is formed in the dot and cross diagram. Okay, now very, very important, get a difference in your brain between halogen and halide. Halogen means salt maker, and it's not surprising they're called salt makers because they're found in lots of different salts and in the sea. So halogen makes the salt, but once it's made the salt is called a halide. So halogen is the element, halide is the ion and the salt. Okay, so chlorine is this, chloride is this. It's got 1 minus charge. Okay, so get that clear. You wouldn't put chlorine on your chips, but you would put chloride on your chips of the sodium variety. Don't put potassium chloride on your chips, you'll poison yourself. Let's have a look at their appearance. Formula: F2, common isotopes, 19F. And it's a light yellow gas. We don't ever use it in the lab. Chlorine, same formula, Cl2, diatomic molecule. 2 common isotopes, as you know, Cl35 and Cl37, and it's a light green gas. Bromine, Br2, it's got 2 isotopes. You don't need to know about it, IGCSE, and it's a red-brown liquid. Volatile liquid. You get vapor of bromine formed above the liquid. And iodine, common isotope 127, it's a grey-black solid. Grey-black solid. Okay. The reactivity of the halogens, well, because they're non-metals, they tend to do things differently than to the metals. So they tend to do the opposite. They gain electrons where the metals lose electrons. So their reactivity actually decreases down the group. If you remember group 1 metals, their reactivity increased down the group. But in the case of the halogens, the reactivity decreases down the group. Okay? So as you get towards the bottom of the group, obviously iodine's not very good at pulling electrons towards itself. So when these react, they have to try and get a full outer shell, so they have to get electrons from somewhere, don't they? So chlorine molecules have to gain 2 electrons, as do iodine molecules. But because chlorine molecules are much smaller, they're much better at putting electrons towards themselves as iodine molecules, other than iodine molecules. Okay? So reactivity decreases down the group. Fluorine is highly reactive and iodine is relatively unreactive. Fluorine is greater than chlorine, greater than bromine, greater than iodine. The melting and boiling points, the larger the molecule, the greater the intermolecular forces. Okay? And the harder it is to melt and boil the halogen. So in the case of chlorine molecules, they're very small compared to iodine molecules. The chlorine molecules have got very weak forces between them, very weak intermolecular forces between the molecules. and iodine molecules have got quite strong, or relatively strong, intermolecular forces. So chlorine is a gas at room temperature, because at room temperature there's enough energy to cause these molecules to separate and these bonds are overcome. But iodine is a solid at room temperature. The general name for these forces, these intermolecular forces, is van der Waals forces. Okay, so displacement reactions of the halogens. Classic reactions that the halogens display. So this is a rule to remember. Any halogen in its molecular form will displace a halide ion from below it in group 7 from a solution of one of its salts. So the more reactive halogen will displace the less reactive halide from its salts. So chlorine displaces bromides and iodides, and bromine displaces iodides. So let's do an example. Chlorine with potassium bromide solution. The chlorine is going to displace the bromide to produce bromine molecules and chloride solution. Now we need to balance that, as you can see. So we put a 2 in front of those two. This is a great example of an ionic equation. So we can get rid of the spectator ions, which are the potassium ions, and that gives us chlorine displacing bromide ions to give chloride ions and bromine. What would you see in this reaction? Well, let's have a look at what we've got. Both of these are colourless solutions. Chlorine water is a colourless solution. It's basically water with chlorine molecules in it. And potassium bromide is a colourless solution. But when we mix them, we get this colourless solution, but predominatingly we get the yellow solution of bromine, aqueous bromine. So you'd see a yellow solution formed. Let's have a look at this in terms of redox. Which of the species has been oxidized? Well, oxidation is a loss of electrons. So you'll see that the bromide has been oxidized to bromine. You can write that down. Which has been reduced? Chlorine. So reduction is a gain of electrons. Chlorine has gained electrons to form chloride ions. Which is the oxidizing agent? Well, if bromide has been oxidized, that means that chlorine is the oxidizing agent. Let's look at the next example, chlorine with potassium iodide. Same kind of idea. That's the balancing. That's the ionic equation. Here, what would you see? Well, you've got a colourless solution and a colourless solution. In this case, we get another colourless solution, but iodine solution is not colourless. It's a reddy-brown colour, isn't it? So a red-brown solution is formed. What's oxidized? Iodide ions are oxidized to iodine because they're losing electrons. Chlorine is reduced to chloride because it's gaining electrons. And the oxidizing agent is chlorine gas. Or chlorine water in this case. Chlorine's doing the oxidizing. And bromine will displace iodide ions because iodine is below bromine in the periodic table in group 7. So same kind of plan. The bromine is displacing the iodide to make bromide and iodine. What would you see? Well, bromine is a yellow solution. Iodide is colourless. And you get a red-brown solution formed. So the solution goes from a yellow solution to a red-brown solution. Which is the species has been oxidized? Well, the iodide has lost electrons to make iodine, and the bromine has gained electrons to make bromide. So the iodide is oxidized and the bromine is reduced. The oxidizing agent here is the bromine. Some extra notes on the halogens. We can show that iodine is present in any solution by adding some starch. It's a bit like the biological test for starch. We use iodine, but in reverse. So when we add starch solution, the iodine turns blue-black if the test is positive. So we can show the presence of iodine by adding starch solution. Iodine is used as an antiseptic, which has an antiseptic smell. Why? Well, iodine is good at killing bacteria. It's good at killing cells in general, so you've got to be careful with its use, but it will kill the bacteria if you get a cut or a graze. And the halogens are also soluble in organic solvents, which is no surprise because they're covalent. So you know that covalent compounds dissolve in organic non-polar solvents like tetrachloromethane or hexane. Bromine gives a brown solution. There it is there. Chlorine gives a very pale solution. I wouldn't even call it yellow, but it's very pale. This is that layer of cyclohexane, and that's a brown solution. So the bromine in aqueous solution comes out and goes into the organic layer. It prefers the organic layer because it's a non-polar solvent, and bromine is covalent. Iodine goes a wonderful pinky purpley color in organic solvents. So iodine will leave the aqueous layer and go into the organic layer, and it forms this wonderful pinky purpley color, which is a good way of seeing if you've got iodine too. So blue-black shows iodine in aqueous solution, and a pink solution in organic solvents also proves the presence of iodine. Right, try the questions from pages 156 and 157 of Essential Chemistry.